Hello my friends of Atari Labs, my name is Sur Montoya. Welcome to this tutorial. This tutorial is about how to create an area of interest raster from control lines with Python and Geopandas. I mean, how can you create a raster without a GIS software? Okay, so for this you need Anaconda, and on Anaconda you need to install Geopandas, Gdal and Descartes, because those are some package and applications that we are going to use. Okay, this can take a while. I strongly recommend that you make a clean installation, because on my case I had Pidal working. I had to uninstall Pidal in order to install Gdal, because there was some conflicts in between the libraries. Okay, if you are in Linux and if you can manage Docker, that could help this. But if you're on Windows with a fresh installation of Anaconda, just install this package and then you will be able to follow this tutorial. Okay, so let's start with a new. You're going to receive on the description of the video a folder that actually will have this, the shapefile, scripts and raster, these are the files that are going to be used, and the script. These are the shapefiles that are going to be used, the scripts that are going to be that we are going to make, and the output raster on the area of interest. Okay, so on scripts we create a new Python 3. Okay, great. And then let's start with the coding. Okay, first of all we are going to create some geodataframes, and then we are going to import some libraries that are Geopandas, Pandas, Matplotlib, and Shapely. Okay, as maybe you know, but Geopandas is also a bunch of spatial libraries, in which Shapely is a very useful part of Geopandas, but in fact it's a library, and it has a lot of tools in order to create geometries, to cut them, to make filters and so on, and we are going to use some of these libraries in this tutorial. So run. Okay, and this command is going to get some lists of the shapefiles that are on the shapefile folder, and then we have some contours, version 2 of the contours, and the area of interest. Okay, these points of the area of interest is in fact an output of the script. Okay, great. Then we are going to open the contour lines and the area of interest as Geopandas data frame. Okay, so with this we open the topography, and this is the shapefile of the raster area of interest. Okay, and this one is in fact like a selection of the first, because there is only one element on this area of interest, and then we get the geometry. Okay, we get the geometry. And for you, if you are new with Geopandas, the geometry, imagine that when you are working in Geopandas, you have like the attribute table, and then another file that is the geometry, that it will be a point, polygon, or line, or multi-polygon, or multi-point, or multi-polyline. Okay, and this is in fact the geometry. In Geopandas, you select only one geometry, and a shapefile can have many geometries, so you have to identify which geometry you are going to work with. Okay, and then we get as well the system of reference. Okay, then in fact this is UTM zone 11 north. Okay, WGS84. Okay, we create a plot, and this is very helpful with Geopandas in order to get a plot of the area of interest, and then of this plot we are going to plot also the area of the topography or the control lines. Okay, and here we have these are not elevation. This is this is elevation, but from the sea surface, so these are actually negative elevations. Okay, but for this it can work for any elevation dataset. Okay, and it can work even with multiple datasets, and this the code you just, I mean, it's not a topic on this tutorial, because this tutorial is intended to be more simple, But if you have multiple topographies, it's possible to work with them with just adding two more, with some more lines of code. It's not so difficult. Okay, so this is the plot. Okay, and then this is the entire extension of the contours, but we are going to work we are going to create the topography just on the extension of this polygon, okay, on the green one. Okay, great. So what are we going to do? Okay, we are going to extract the vertices in this polygon, okay, and this is very important. We are going to extract, yeah, with this we create a new data frame, and then for every, we do some smart filtering here, okay. So for example, if you have a geometry or like a line that is invalid, actually it won't make any process, so it will pass, okay. And if it will try if the line if the line crosses the area of interest, it will create a simplification of the line. But if the line do not cross the area of interest, actually it won't make any, it will pass, okay. So with this line actually filters all lines that do not cross the polygon, okay. So, and for the lines that crosses the polygon, we create a simplification, because actually the isolines have lots of vertices, and for our interpolation, this high amount of vertices for each contour line could decrease the level of the interpolation. So actually we create a simplification. You can do more simplification. For example, it really depends on you. If you select in between 5 to 50 or 5 to 100, it depends on the accuracy, and not only on the accuracy, but on the final density of points of vertex that will be. If you have lot of vertices on a contour line, the interpolation will try to create some some flat zones, while if you have few vertex on the contour lines, at certain level you can have more like a more dispersed distribution of your data, and then your interpolation will be more uniform. Okay, so you have we are going to print the amount of vertex before and the vertex after, in order to see the reduction, okay, because we want to see which is the reduction on the level. But because this is key when you might need to do that for like entire extension, or like if you want to do that for dynamic topographies, okay, you want to see how much you are going to, which is the reduction of the data sets by the simplification, okay. And on the simplified lines, for every chord, yeah, if the chord is inside the area of interest, it will create a new point, yeah, a new point. It will create a new point with the attributes of eastern, northern, and elevation, and also the ID, okay. And for every 1000 vertex process, it will print some values, okay. And then we are going to have the head of the resulting database. This, for these data sets, it actually do not take so long. If you have like a very heavy data set, can take longer, okay. The advantage here, and can take longer for this for which one, for for the iter rows. I don't know why this iter row is not faster. I mean, my experience with pandas was great, and maybe this was the only time that I got such amount of time expended on this process. Okay, but the advantage is that you can automate this. I mean, it doesn't matter if you want to do this on a very automated way. It's actually possible, because in fact, I mean, if the loop or like the type of amount it has more than maybe 10 times the size of this, it will take maybe 10 times longer, but in the end you just wait and then you get your raster. Okay, so, and these are the vertices process, and this is, for example, for this we have 3000 vertex. After simplification we have 1000 vertex, and the reduction rate is this. Okay, and very interesting that just for these lines actually do cross the area of geometry, but the other lines actually do not cross the area of geometry, therefore no process is done. Okay, and this is our this is the head of our Geopandas data frame, easting, northing, and elevation, and the geometry. Okay, then we can plot the contour lines, the raster, the reference, and the points, and the geodata frame. Okay, here we have the contour lines, the original. Here we have the point data frame that are actually point wise, but maybe you don't see it very clear. And then you have the area of interest. Okay, we can export the point to shapefile, because we might want to see this in the shapefile, because in the end we are going to compare this on GIS. Okay, so therefore we need to export them. Okay, and then we are going to do some point interpolation. Okay, and this point interpolation will be done with Numpy. Okay, we create a grid, we create the points, the x and y, we create the values, yeah, we use a SciPy interpolate, yeah, we have a raster resolution. Okay, we print the bounds. Okay, and we define the number of columns and number of rows. Okay, so with this we see that for 100 actually we have well, we can have, those are float, but those are integer values, so 210 and 130. Okay, because let's see, like you have this 80, actually those are not integer values, and the code is not adapted for that. I could make the code adapted for that, but in this case it's better that the dimensions of your raster are multiples of the raster resolution. Okay, great. Then we create some rasters. We create some rasters, and then we do the interpolation. The interpolation is just done with this line. So we create the raster of the y values and the raster of the x values, and then we create, and with this we have the interpolated values, but these values are just as a Numpy array. And if you want it as those are just as a Numpy array, and we can have a representation of the raster, but as an Numpy array. I mean, this is the representation of the interpolation, but as an array that goes from 0 to 130 and from 0 to 200 something columns. I mean, 130 rows and 200 something columns. Okay, but you might need to do it as a raster because you wanted to work with this on a GIS software. Okay, or you want to do some geospatial analysis where you require this as a raster. Okay, and then we create some with Gdal. Okay, let me see if this works. Okay, yeah, this works. Yeah, from OSGeo import Gdal array and reference values, and these are just the setup of how you transform this in a geospatial raster, and then you create a tiff with this number of columns, this number of rows, and then you select that this will be float 64. You apply the geotransformation, you define the system reference, then you add the elevation value to the raster, and then you close the raster, because actually otherwise the raster will be kept open and then you cannot see in GIS. So with that, okay, that's it. You don't need anymore. When you open QGIS, okay, this is QGIS, and here we have the contour lines. Those are the contour lines. Yeah, I can define or can apply some styling in order to show the okay, contour, classify, loose, apply, until apply. Then we create some labels: contour, buffer, text, apply. Okay, and here we have the contours. Okay, and then we can plot the points that are we can plot the area of interest, that is this one. No, doesn't look so pretty, but it's pretty in the end. Okay, and then we can plot the points, I mean the extracted vertices of the simplified version of the isolines that are intersected of the area of interest. Okay, great. And from this, yeah, I can plot the raster, like the area of interest raster. Okay, and this is the area of interest raster, and then I can apply some more beautiful single solo color. Okay, great. And then I can put this here. And for example, if I inspect, for example, here, as a table, here we have some points that have minus 570, and the contours also have minus 170, and the area of interest raster, that is the output, also is minus 570. Okay, and let's see if this is actually, this is the upper part. Okay, where we have the extracted values have a minus 240, the contours are also 240, and the raster is minus 239.1. okay, and this is very pretty close. And let's see in this. Okay, we have from the extracted point minus 400, from the contour minus 400, and from raster is minus 399. Okay, so as you have seen, the procedure is pretty automatic. It works for every area of interest. I strongly recommend to do the raster with the data provided on the to replicate this tutorial. And it took me some time to develop this tutorial as well, so it's actually quite not for dummies, but I hope that you find the procedure, like you find the that you can find the value of this for your own work, okay? And then you can automatize your work, and then you can create better rasters, and then you can do more analysis, okay? And then you have better tools to do your research. Okay, my name is Saul Montoya. We're from Hatari Labs. We have a lot of tutorials based on spatial analysis, numerical modeling. Hope that you can follow us, follow our YouTube channel, and if you like what we do, just share it through your social networks. And I hope to see you in coming tutorials. Bye bye. Bye. Remember that all the files and all the scripts are in the description of the video. Bye bye. Bye.